Section 2.3. In Chapter 2, in the first two sections, we have investigated solution techniques for two distinct types of first-order differential equations. First, we looked at linear first-order differential equations, and then we looked at separable first-order differential equations. To summarize our approach to these two types of ODEs, in order to solve linear equations, we had to first construct an integrating factor called mu of t, and then we followed a pretty elaborate process that involved identifying the structure of the product rule on the left-hand side of the equation, and then following the necessary steps. In contrast, separable equations felt a little bit more straightforward. We simply separate the variables and then integrate both sides. In this section, we introduce a type of first-order differential equation called exact equations. The approach that is required to understand and solve exact equations is very different from the approach of the first two sections. I would strongly encourage you to pause the video right now and carefully read through the rest of the notes for this section. Then return to the video and listen to me explain, and hopefully through that whole process, the details will make sense. This section is very conceptual, and it's very different from the first two sections in this chapter. So I just give that little word of warning because what I have to explain in this section will feel very different from what we did in 2.1 and 2.2. In order to understand exact equations, we must understand partial derivatives. There's a chance that some of the students in this course have not been taught partial derivatives. And so what I need to do in this section is give a brief overview of partial derivatives and then explain how those define the structure of exact equations. If you're unfamiliar with partial derivatives or you simply want a review beyond the detail that I provide in this example, I would encourage you to take a look at our author's textbook for Calculus 3, and I provide a link here that'll take you straight to the section which describes partial differentiation. So let me start this section by giving an overview of partial differentiation. First, I would like to contrast partial differentiation with the type of differentiation that we're more accustomed to. So think back to Calculus 1, Calculus 2, as well as all of the math you did prior to calculus. And in all of those courses, you dealt with functions which had one independent variable. There was a single input for the functions that you dealt with. Think of some classic examples from calculus. I've listed a few here. F of x equals sine of x clearly has a single input variable x because it has a single independent variable. The same is true for these other functions. In contrast, consider functions like these that I've listed here. This first example is f of x comma y equals x squared minus 2xy plus 3y squared. Now this function has two independent variables. Two inputs are required in order to evaluate this function. And those two inputs are manipulated according to the formula provided on the right-hand side. The same is true for these other examples. In this paragraph, I try to just reiterate that point, that in order to evaluate these types of functions, we need to provide multiple inputs because there are multiple independent variables. Just as an example, think about this function a of mn. It wouldn't make sense to ask what's a of 2 because I have no way of determining whether this 2 should be a value for the variable n or a value for the variable m. I said those backwards, but you see what I'm saying. Instead, we need to specify two inputs, specifically two inputs as an ordered pair, one for the variable m and the next for the variable n. Functions like the ones that I just described are often called multivariable functions. And when it comes time to differentiate this type of function, our classic single variable derivative won't suffice. Instead, we must take what are called partial derivatives. Partial derivatives can be defined formally in terms of limits, and in the context of a Calc 3 class, we would go into that detail. Here, I just want to give you the main idea. The fundamental idea behind a partial derivative is this. When you compute the partial derivative of a function with respect to a specified variable, we treat all other independent variables as constants. Let me say that again. If I'm going to compute a partial derivative with respect to a particular variable, the way that I do that is differentiating using my standard derivative rules, but the key is I need to treat all other independent variables as constants. It's important to reiterate that when I calculate a partial derivative, I must specify which independent variable I'm differentiating with respect to. This is demonstrated in the notation that we use. This fraction here indicates the partial derivative of f with respect to x. Notice that in my denominator I have a delta x. That signifies that I'm differentiating with respect to the independent variable x. In contrast, this fraction would signify the partial derivative with respect to y. Sometimes this delta notation is a little tedious, and so an alternative notation would be to indicate the variable we're differentiating with respect to by putting it in the subscript. So this f sub x indicates the partial derivative of f with respect to x. And this notation is pretty common, so that's the main notation that we'll use. Let's demonstrate how partial differentiation works by taking a look at a couple of examples. For example number 1, we're provided with a multivariable function f of xy equals x squared minus 2xy plus 3y squared. We're asked to calculate several partial derivatives. First derivative we're asked to calculate is a derivative of f with respect to x. According to the idea that we highlighted a second ago, when we calculate this derivative, we will use the standard differentiation rules on the x terms. For example, I know that the derivative of x squared is going to be 2x like it usually is, but I also accommodate for the other independent variable by treating it as a constant when I'm differentiating with respect to x. So in order to evaluate this derivative, I need to treat the y's in my function definition as constants. Just to be extra clear on this first example, over here in the margin, let me rewrite this from a slightly different perspective. In this right-hand margin, I've rewritten the function, but since I'm differentiating with respect to x, and I will therefore be treating y as a constant, I've actually rewritten the function so that the y's are represented as a constant. In this case, I picked k. So I could imagine a Calculus 1 problem where I'm given a function of this nature, and I'm asked to find its derivative. And that would be a relatively straightforward calculation. Calculating that derivative using the standard differentiation rules, derivative of x squared would give me 2x. The derivative of negative 2x times a constant would be, well, I would be differentiating it as if it was x to the first power. So the derivative of x to the first power, I'm just left with the constant on that term. And then this 3k squared term, if k is a constant, then when I differentiate it, I get 0. This is not the actual function that I'm differentiating, but I just write this for reference to kind of give you the perspective that when I'm differentiating with respect to x, when I see y's in the statement of my function, I will treat them as if they were k's, for example, or some other constant, and then I apply my standard Calc 1 derivative rules. As such, I can calculate the partial of f with respect to x, and I will get 2x minus 2y. Next, we're asked to calculate the partial of f with respect to y. In this part of the problem, I'll return to my original function and differentiate that function. But this time, since I'm differentiating with respect to y, I will be treating x as a constant. Adopting this perspective and applying my standard differentiation rules, the derivative of x squared will be 0, because with respect to this derivative, that x squared term is constant. The derivative of negative 2xy will simply be negative 2x, since I'm thinking of the y as a y to the first power term, and then the 2 and the x are both being treated as constants. And then the derivative of 3y squared will be 6y, as I would expect. In part C, we're asked to calculate f sub x. To clarify this notation, I will calculate the partial derivative of f with respect to x. That's my answer from part A. And then to that derivative, I will again apply the partial derivative with respect to x. So another way of writing this is to say I will apply the partial derivative with respect to x to f sub x. As I said, I already have f sub x, the partial with respect to x, from part A. So I could think of this as applying the partial derivative with respect to x to my answer from part A. Since this is a derivative with respect to x, this derivative treats y as constant. So applying my standard differentiation rules, the derivative of 2x will simply be 2, and then the derivative of 2y will be 0, because with respect to this derivative, that term is constant. Parts D and E also ask for second order partials. So let me again start by clarifying this notation. This is asking for f sub xy, which means I should take f sub x, the partial of f with respect to x, and then apply the partial with respect to y to that expression. So rewriting that in a slightly different notation, I will take the partial with respect to x, that's my answer to part A, and this time I will apply another derivative to it, but I'll be applying a derivative with respect to y. Adopting the perspective now that x is a constant, applying my standard differentiation rules, I get the derivative of 2x will be 0, and the derivative of negative 2y will be negative 2. I have one last partial derivative that I'm asked to evaluate in this example. Expanding my notation again, I notice that in this part, I want to first take the partial with respect to y, and then apply the partial derivative with respect to x to that. So here I've written that out. This inside derivative is my answer to part B. So I'm going to take my answer to part B, and then I will apply a derivative with respect to x to that. So here's my answer to part B. I'm adopting the perspective that I'm differentiating with respect to x, so that implies that this y is constant, so this derivative will simply evaluate to negative 2. The fact that my answers to part D and part E are equal is actually very important. It's not a coincidence. This isn't necessarily true for every possible function, but if my function is nice enough, then I do expect these, what are called mixed partials, to be equal. We will return to that fact and utilize that fact to understand the structure of an exact equation later in the lecture. Now that we've seen an example of how partial differentiation works, it's natural to ask if reversing the process will act similarly. And this paragraph here indicates that so-called partial anti-differentiation does work how you would expect it. But there is one additional detail, or one specific detail, that we need to pay careful attention to, and that's the constant of integration. So typically when we anti-differentiate a function, we're accustomed to adding a plus c at the end to account for the fact that the antiderivative could have a constant at the end. The way that plays out when we're dealing with partial derivatives in functions of multiple variables is a little tricky. So we're going to try to demonstrate that in, for example, 2. In this example, we're going to consider an expression 2x plus 8y minus 6xy. What we want to do is we want to imagine that there's some unknown function, say capital F of xy. From now on, I'll just refer to it as capital F. And this is an unknown function such that this function f and our expression have a specific relationship. Namely, we want to assume that this expression is the partial derivative with respect to x of the unknown function f. If that's true, or if we're going to make that assumption, then I can back up from the derivative up to the original function by anti-differentiating with respect to x. We'll write this in a couple ways. Sometimes we'll simply say f sub x equals 2x plus 8y minus 6xy, and then we'll just indicate that that implies that capital F equals the appropriate expression. Sometimes we will actually write the derivative expression and then introduce an integral with respect to x to the entire equation to indicate that we are anti-differentiating with respect to x. In either case, the anti-differentiation process acts more or less how we would expect. I have 2x, and if I was asked to anti-differentiate that, I would be accustomed to saying that the antiderivative would be x squared. The antiderivative of this 8y term may be a little tricky because I have to bear in mind that I'm anti-differentiating with respect to x. So with respect to x, this term is constant, and so its antiderivative would be 8y times x. I'll write that as 8xy. And then this third term, when I anti-differentiate it, I again treat y as constant. So since the anti-differentiation process that we're doing now is with respect to x, and I simply look at the 6x, I would add 1 to the power, divide by the appropriate power, and this term becomes negative 3x squared y. But, as I just mentioned, anytime we perform anti-differentiation, we are accustomed to adding a constant of integration, a plus c. In this context, unfortunately, it's more complicated than that, and I want to demonstrate that. The important idea is that if we went backwards from this capital F to its partial with respect to x, that differentiation process would treat y as constant. Therefore, this constant term, quote-unquote constant term, could potentially contain y values. Let me try to demonstrate that by looking at a few examples. Suppose each of these three functions is a candidate for the capital F, the antiderivative or the original function that I'm trying to recover. These functions are the same if we focus on the first three terms, but in this first capital F, I simply have a constant added at the end. In the second capital F, I have a y cubed term added at the end. And in the third capital F, I have quite a few terms. But notice that these extra terms in the third F are all strictly in terms of the variable y. As such, and you should check this yourself, if I was to take the derivative of any of these with respect to x, the resulting derivative would be the same for all three of these functions. That is to say, these highlighted terms in each of these three functions, when I differentiate with respect to x, will all be considered constants. Therefore, the derivatives of all of these highlighted terms with respect to x will be 0. And so they'll all yield the same partial with respect to x. This means that if I ever start with a partial derivative and try to work backwards to recover the original function, then I have to account for this ambiguity within the constant of integration.